All right, let's get through chapter 16. Abhishek, Madeline, Manny, Manny again.
Okay, sorry.
All right, cool. All right, so chapter 16.1 for section 16.1, vector fields. That's just pretty much introducing, what is a vector field, and it's just a function that tells you at its given point x, y, and z, you have a vector associated with that point, right? So that's nothing new. That's something like hard to grasp conceptually. So like drawing vector points, vectors at a specified point in a vector field, that's fine. A unit vector field is just saying that the magnitude of all these vectors is 1. That's also nothing new. Like we know like a unit tangent vector is a unit normal vector, etc. So conservative vector fields and testing for that and also finding the potential function, that's where it gets like actually more like challenging and hard to like grasp. So we're just going to kind of like backtrack into like what a vector field is. So if a vector field is to be conservative, it has to have a potential function. And what that means is that your vector field that you have, it's not just randomly assigning vectors to points in space. All those vectors have a pattern to it, and the pattern is the potential function. So what that means is that your vector field or your vector field is going to be the gradient of the potential function, meaning that the potential function is, you take the partials with respect to x, y, and z, and those become your x, y, and z components of your vector field. So then the question becomes, how do you test for that? That's when you do the cross partial equalities to either prove or disprove if a vector field is conservative or not. And I think that maybe might have done a derivation in class about like where that came from, but it came from Clairaut's theorem, which had stuff to do with like the gradient and like the cross partials. But so pretty much all you want to do is you want to take your partial with respect to x of the potential function, which is this first component of the vector field, and you want to cross that with y, and then you want to take the partial with respect to y and cross it with x, and then do that for all of the variables. We're not going to talk about curling. Yeah, what's up?
Would that mean that you do like 3 of those?
Yeah, for 3 dimensions. Yeah, I'm actually going to skip over to 16.3 right now because like 16.1 and 16.3 are kind of like the same thing in my head. So we'll just go ahead and do that. So talking about conservative vector fields again, how do you determine if a given vector field is conservative? You do the cross partial inequality. That's definitely a possible question, like prove that this vector is conservative or not conservative. And then the second part of that is obviously, if it is conservative, what is the potential function? Yeah, so that piece. So we know that if a vector field is conservative, first and foremost, the cross partials will equal each other.
Wait, can you just slow it down?
Oh, sorry. The cross partials would equal each other, but we also know that the vector field has a potential function. That's and if you think about it, that makes sense. If all of these vectors have a pattern to them, they're going to be conservative because like the next piece of a conservative vector field is that you can, if you start and end at the same point, you've effectively traveled a certain path, gained some kind of like work done or some other third variable, and then come like right back. So you've like gone negative, like displacement back. Like if it helps you guys think about conservative vector fields as a state function, that's like definitely helpful, but it's not really that necessary because the fundamental theorem of conservative vector fields kind of takes that into account. And so it's pretty much saying that the integral along the line, so the line integral of the curve C of your vector field is just going to be the difference of the potential function, like the final final minus the initial points.
Of your conservative
If it's, wait, what?
method. Of your conservative.
Yeah, and this only applies for conservative vector fields, and that should be self-explanatory because it's the fundamental theorem for conservative vector fields. So, so one thing to keep in mind, kind of as a potential area that could be tested on that might get like a little tricky, is prove a vector field's conservative. We know how to do that. You just do the cross partials and see if they're equal to each other. Find the potential function. You just integrate the x, y, and z components with respect to those variables, and just circle the unique pieces. So that's all easy, and we've done homework problems like that before. But something that could be new or challenging, or a next level type of question, would be, in addition to all that, specify the domain of the potential function. So you have to keep in mind that for the fundamental theorem to be used, to just plug in the last or the final initial points into your potential function, your domain has to be simply connected. Meaning that, referring to this picture, this is just a paraboloid facing downwards. It doesn't have any holes or cracks in it or anything. So this this line integral that we're doing, that we're simplifying using the fundamental theorem, is connected, and it's over a domain that, like I said, is simply connected. Doesn't have any holes in it or anything. Does that make sense? I know we didn't spend a lot of time on that in lecture. Okay, cool. Qualities, potential function. All right, so that's pretty much it for 16.1 and 16.3, talking about vector fields. And the last objective on 16.3 is using the fundamental theorem. And I personally like to think about it as an extension of a state function. If that works for you to consolidate that's great. If not, don't worry about it. The formulation is pretty easy to remember, just final minus initial. All right, questions on 16.1 or 3? Okay.